guys, this is Li Xuanfeng from Xiamen University, Malaysia, and this is a MAT 101 project for me to talk about the quaternions as a non-commutative number system. Let's talk about what is commutative number system. A commutative number system allow A times B is equal to B times A. Well, a very easy example is 1 times 2 is equal to 2 times 1, and they both equal to 2. So what is non-commutative number system? There's a none in there, so it's basically A times B is not equal to B times A. A very classic example to show the non-commutative number system is matrix A multiply the matrix B is not equal to matrix B multiply the matrix A. And our topics today, the quaternions, is also one of the example for the non-commutative number system. So before we very talk about the quaternions, let's talk about the complex number. A complex number can be written as Z is equal to A plus BI, where A is a real part, while B is an imaginary part. And yeah, the Z can be written as it's not written, it can be represented as a vector or a coordinate in these diagrams. If there is a horizontal line, the coordinate is R0, while it rotates an angle of theta, and this is the result. And this shows complex number is actually useful for our real life. It's actually talk about the rotations, and complex number is actually talk about the rotation in 2D, which is a plane. And we know cosine theta is actually the adjacent divided by the hypotenuse. So it's A over R is equal to cosine theta. And we multiply both sides with R, then we will get this result. Sin theta is the same thing. Sin theta is B, which is the opposite, divided by R, the hypotenuse. And we will get the result R sin theta is equal to B. While we can written the complex number in a new form, which is directly involved into the theta. And this is something important. Z is equal to R cosine theta plus I sin theta. Because this can lead to another form also. Euler formula. Yeah, these are very interesting stuff. You know that the Taylor series of the transcendental function Ex is this way. For the further details for the Taylor series, if I were free, then I will make a video for this. But right now we are focused on the quaternion, so I just roughly talk about this. E to the power x can be written as this way. You just this is a polynomial approaching, I would say. And cosine theta, the Taylor series expansion can be written as this way. What if we let x equal to I theta? E to the power I theta can be equal to this stuff. While the power for this power 1, power 3, power 5, they are actually, because we know I power of 1, I power of 3, I power of 5 is actually complex number, is still imaginary. It's I minus I, and so on. So the odd power number is actually the imaginary part, while the even power for I, something like I theta square is actually, we know I square is minus 1. So I theta square is minus theta square. So while we multiply I in here, you get something like, wait, something so familiar. Yes, this is exactly the same, while this one is the same thing. So we can return the e to the power of I theta in terms of cosine theta and sin theta. This is a very beautiful way to talk about the rotations. Well, what does this mean for the equations? This means there is a vector in 1, 0. I think I can just here 1, 0 is here, and it rotates an angle of pi, then it will become e to the power of I pi. Is e to the power of I0. So from here, we know that complex number can be talk about the rotation in a plane is actually 2D. So does it commutative? Okay, let's see. Let's see, does it commutative? If there is a vector, this both side, uh, we can just ignore the coordinate of this vector. We just don't know the length. It doesn't matter, but the result is important. If this vector rotate angle of theta 1, it becomes this S N not B naught, the coordinate. While it's rotate another theta 2, yes, we get this A2 B2. And we can write in this way. And but if we rotate theta 2 first, then rotate another theta 1. This is the same thing, right? We just changing the order. But we know that theta 1 plus theta 2 is actually equal to theta 2 plus theta 1. Pi over 2 plus pi over 4 is actually equal to pi over 4 plus pi over 2. So since the addition is commutative, so we can conclude that this result is actually the same. So this shows the commutative property in 2 dimensions. What about 3 dimensions? So let's just assume there is one more axis, Cj. Okay. I know it's wrong, but let's see why it's wrong. Okay. If there is something like J, we have to define something like I multiply J is what? We know in 2D, we can define I squared is -1. But what if we define Ij is -1 also? Okay, we multiply both sides with I, and we will get I squared is equal to J, I squared J is equal to -I. And we multiply I -1 both sides, we'll get J is equal to I. It's not weird. Yeah, it's weird. But let's see why it's weird. Initially, we are inventing the 3-dimensional system for the AJI. AIJ is same thing, but what we get actually is the result I is equal to J. This J axis becomes a I axis. Then instead of saying we are inventing 3-dimension system, we are just making the 2D stuff. There's no difference compared with the IA, the view. So yeah, this turns out a result why trinomials is filled to describe the 3D rotations. If we wanna do something like the 3-dimension, each axis must be linearly independent. So what if we add more dimensions for the system? Instead of saying the AIJ system, we can make it into AIJK. Yeah, but we don't go it too fast first. We just see what if ij is equal to a vector k, and they are both linearly independent. They are not both, they are all linearly independent. So we can see from here the ijk is actually something similar to the xyz plane. And this system is not collapsed. Yeah, it's not something like, we wouldn't get something like I is equal to k or I is equal to j. It doesn't get something like weird result. So we will get a system like, we just call it Quaternions because this is Quaternions as a q is equal to a plus bi plus cj plus dk. So there is another axis. So yeah, since this one is shares some similar property to the xyz plane, so we can use the cross product. Okay, so well, let's see what is a cross product of ij. We found that the I cross product J is actually K. And what if J cross product with I? There is a negative sign. There is a negative sign. This is very important. Why is important? Because just now we said that a commutative number system is A times B. A multiply B is equal to B times A.